Okay, so new thing for today. Let's see, here we are in the fourth week of classes, and we're going to finally get around to defining what you might reasonably call a multivariable derivative in a class called multivariable calculus. Right? So, yes, it took a long time to get here, but we have most of our groundwork laid. Multivariable functions, vectors, which are going to be, of course, a big tool in understanding the multivariable context in general. So, what is a derivative? So it turns out there's actually lots of different answers to that question. There's not just a single kind of a derivative. There's a bunch of them. There are, different ways to look at all of them. So, before we get into specific derivatives and specific interpretations, I want to lead with, I think this is a really big idea for how to think about all multivariable derivatives. Ultimately, what is a derivative? What do they all have in common? What is it about them all that we can reasonably use the same word, at least as a category, to describe them? And so here it is. It's a relationship between changes in the input to the function and changes in the output of the function. So that's what it is. They're all of the different kinds of derivatives that we're going to talk about. They all have this common feature. They are in some way or another a relationship, a connection, whatever, between input changes and output changes. So please try to keep that in mind as we go through and talk about a bunch of different kinds of derivatives in the next couple of weeks. Okay. All right. So we're going to start with something called partial derivatives. Some of y'all might have even seen partial derivatives previously. We start with partial derivatives. This is my opinion at this point. But I think the reason we start with partial derivatives is because they're relatable. They're going to seem a lot like single variable derivatives. And because they're easy. And it's a nice sort of first step into the water, dip your toe in kind of a deal. And that's good, right? These are all fine. I'm all for it. There is a disadvantage, and again, my opinion, disadvantage to starting with partial derivatives in that it kind of implicitly suggests that partial derivatives are, fundamentally, that's the how you should think about derivatives in a multivariable context. I mean, after all, that's what you're starting with. That seems to be the implication. And I think that's a bad idea, right? So I'm going to call this a warning. I don't feel that you should hang your hat on partial derivatives as, foundationally, cornerstone, how should you think about multivariable derivatives. Okay, so don't buy in too much, if you will, to these partial derivatives, even though we're starting with them, right? We're starting with them again because they're easy. They're relatable and they're easy, and that's nice and all, but there's really better to come. Okay, so that said, all the sort of warnings and context being done, suppose you have a multivariable function, f. Okay. The way you compute a partial derivative is you hold all of the input variables constant except for one, right? And then view the result as a single variable function. And then just take a derivative. All right, so now let me lay that out a little bit more specifically. When we say hold all the input variables constant except for one, x1 for the purposes of this calculation is not going to change. x2 not going to change, et cetera, et cetera, et cetera. And then from the other side, xn not going to change. Xn minus 1 not going to change. Only one of the input variables are we going to allow to change at all. All of the other input variables are going to be just nailed to the floor. They're not allowed to change at all. x1 fixed. x2 fixed, etc. And this is going to change our point of view on what f really is. I mean, let's just hit the pause button here. What is a multivariable function? A multivariable function is a function where there's lots of different inputs that are allowed to change, and depending on what all those different values are, we get some outputs. And I'm saying that if you come to me with such a thing, I'm going to fix all those input variables, except for one. So if they're not allowed to change, they're kind of not really variables anymore. Know what I mean? Right? They're fixed. You might as well call them K instead of Y. If Y is not allowed to change, it's not really that different from a K. So ultimately, then, what remains, having done this thing where only the one variable is allowed to change, it really is a single variable function at this point, for the purposes of this calculation that we're doing here. Okay. And that single variable function, if you want to write down the derivative of it, well, that single variable function's derivative, this is just plain old single variable calculus, right? Single variable derivative of a single variable function. So this is what we call a partial derivative. This is our definition of a partial derivative. You'll notice the notation is a little different. These little things here, they look kind of like D's. They're supposed to look kind of like D's because we're kind of thinking, df, dxi, a la single variable calculus. But very importantly, I cannot write in place of this. I cannot put df dxi, because this notation means something, right? That notation means f is a single variable function of only xi, and that's not how it came to us, right? F came to us as a multivariable function. It is after it came to us that we decided that we wanted to do a certain thing to it, the first step of which was to fix some of the variables. Right, so it wouldn't really make any sense to use that notation. It'd be a little dishonest. So this new symbol here, that new symbol, the partial symbol, is intended to be deliberately a little bit different, but also pretty recognizably similar. Okay, everybody on board so far? Okay, by the way, two more things about this symbol. This symbol is also not the same as the lowercase Greek letter delta. Not the same. You cannot use delta. Sorry, absolutely not the same thing. Right? So you got to be careful with that. And again, you cannot use D either. I mean, there are some contexts, some high school contexts, where teachers will say, whatever, don't worry about it. It's, who cares? It's really not okay. Right, so you've got to make sure to not do that. And the other awkward thing I'll mention while we're on the topic of notation is making this little thing. It's a new character, right? Y'all probably never made that. Many of you anyway have never made that little symbol before, and so this is a little bit silly and embarrassing even. But it's almost like you have to kind of now rewind and go back. How did I learn to make the characters that I am accustomed to making? Well, in second grade, they made me sit here and do that over and over again. So, fill up a page, right? I mean, again, it seems a little sort of humiliating and ridiculous, but think through, are you going to be the kind of person that goes around like that? Or are you going to be the kind of person that goes around like that? You got to decide. Pick a camp, right? I'm not judging, right? But you kind of have to decide. And be careful not to accidentally make it look like a zero, right? So it takes a little practice to get good at this. Okay. All right. So let's compute something. And this is going to look like a hard problem to start off with. But let's take the y partial, we call it, of this great big monstrosity here. And wow, there's several factors, one of which is a composition involving an annoying trig function and a product that has exponentials in it. And wow, this is going to be a pain, right? Okay, but make sure to remember, when you're taking a partial derivative, that variable that you're taking the partial with respect to, that is the only actual variable. So y is a variable, and all of the other variables are constants. So this x right there, constant. This x right here, constant. That z, constant. In fact, what I have here is y squared times a great big constant. And that derivative is easy. Right? X and z constant, right? All that's constant. the derivative is just 2y times that same constant. Everybody on board with that? So by the way, I nominate partial derivatives as being the easiest kinds of derivatives to compute, even easier than single variable derivatives. Because when you're taking partial derivatives, you get to use all the same rules that you could with single variable derivatives. And furthermore, you get to just kind of ignore, I'm going to pretend like that's a constant, right? Huge tracts of the function that you're dealing with. You just, a constant. So it's even better in terms of convenience. Okay, a couple more examples. I'm going to go kind of quickly through these because this is just, sort of observation. But it feels a little weird the first time you do a question like this, taking the x partial. Now, this one looks scary. You've got a function to the power of a function, and how do you take a derivative of a function to a power of a function? Quick little side note. Does everybody remember logarithmic differentiation? Show of hands, just curious. Logarithmic differentiation. Very few. Wow, few of you do. Okay, all right. But logarithmic differentiation is a neat trick. It's a cool tool in single variable calculus. And unfortunately, it seems a lot of high schools are kind of cutting that out of the curriculum. It's not that big a deal. It's not hard to do, and it's very powerful. And I think you'll have a difficult time. And if this question were to compute the partial with respect to x of x squared plus 1 to the power of x, that's a really hard problem if you don't know logarithmic differentiation. And if you do know logarithmic differentiation, it's not bad at all. So I'm going to encourage everybody to, if you have seen it or are a little rusty, brush up. If you haven't seen it before, look it up. It's not that bad. By the way, I have a video on logarithmic differentiation. It's on my YouTube channel. It's in the miscellaneous topics playlist. Title of the video, I think, is logarithmic differentiation. It's like a 20-minute little quickie. You can probably fast forward through a lot of it. So, anyway. So that's what this feels like. Again, at a glance, you look and you see a function to the power of a function. What can I do? This isn't a power rule problem. This isn't a exponential problem. Or is it? Keep in mind we're taking a partial with respect to x. So x is a variable, but all other variables are constants. That means y is a constant. That means you play the same game that you... This is, in fact, a power rule problem. It just doesn't look like it. And it feels really wrong somehow to do that. The first time you write this down, you're going to be like, oh gosh, this does not feel right. But it's right. Okay. Likewise, here, taking a partial with respect to z is the variable, everything else is a constant. That means this thing here is a great big constant. I have a constant to the power of z. This is an exponential derivative. And you just use the good old exponential rule, right? The derivative of an exponential is that same exponential, and then times the natural log of the base. So, okay. All right. Sometimes, you still got to do a little work. Here we have a y partial and y being the variable there and there. Do notice that it remains that I have a product. So I do still have to use the product rule. Right? Details for y'all to walk through. But good news is you do still get to use the product rule. All right. Okay, moving along. I just wrote down something algebraic. I didn't address the question of what is this geometrically. By the way, you should, again, always be a little suspicious. Sometimes, if you write down an algebraic definition, sort of copying from a previous algebraic definition, does this still mean what it used to mean, or is this totally different and makes no sense anymore? Right? And just because we write something down algebraically doesn't mean it's actually useful for anything. Right, so I owe you an explanation of why is it that this is geometrically natural or physically natural, or does this relate to anything at all, or am I just writing down nonsense? Okay. So it turns out to be pretty easy to answer that question. Let's think about this in the context of graphs. Reminder, if you're looking at a function from R2 to R1, what does the graph of such a function look like? Well, the domain, when you're making a graph, like that. The target, like that. Remember, the idea of a graph construction is you put the input variables and the output variables on the same axis system. Typically, we put the output variable vertical. And then on this picture, you make plots, x comma y, in this case, x comma y comma z. And so our graph is going to be some surface like that, defined by that equation right there. Okay, so in this setting, let's just talk through what are we doing geometrically when we go through this algebraic process of taking a partial derivative. And this time, just to get it started, let's talk about partial with respect to y. So partial with respect to y means that I'm going to view y as the only variable. That means that my other variables, in this case, there's only one other variable. The other variables are fixed constant, right? So x is going to be fixed. I am not allowed in the domain now to leave that line. X is constant. Okay, let me come down here where I can see better. So y is the variable. That means that, in fact, I'm confined then to, y being a variable. This is how I'm going to be moving, right? Again, stuck in that line. In the graph world, that means that I'm stuck on this plane. How does a plane relate to a graph surface? Well, it takes cross-section, right? So what I previously had been interested in this whole graph, this whole surface. Now I'm interested in what do you get if you look at that graph, but also with the understanding that x is fixed. So this combined with that, just that curve. Just taking literally the cross-section, a vertical cross-section of that graph. Right, and then, having done that, we take the derivative with respect to y. Namely, with respect to my only actual remaining variable. And derivatives, in this graph setting, where I've got, the value of the function, represented vertically, right, as a function of my input variable, which is going horizontally. Where do I know what derivatives look like? In that setting, derivatives are the slope of the tangent line. And so there's our geometric interpretation of the partial derivative. Geometric interpretation of the partial derivative is, I didn't want to erase that. The geometric interpretation of the partial derivative is that you look at a cross-section of the graph appropriate to which partial derivative you're taking. You look at that slice of the graph. You look at the tangent line to that cross section of that surface, which is the graph. And slope, rise over the run, is the partial derivative. So as I have drawn here. So there you go. The partial derivative is the slope of the tangent line to the part of the graph in the y direction. Okay, everybody on board? Now, a couple observations I'll make while we're here. That is very naturally geometric. It's a slope of a line, right? Tangent to a surface, right? That's all geometry talk, right? It's also very familiar, right? Slope of a tangent line, that was our sort of at least in high school classes, that's the sort of primary point of view that's presented for what a single variable derivative is. So very relatable, very familiar, and again, already observed, very easy to compute. So partial derivatives are really great in a lot of ways. Okay, I'm going to leave it as an exercise for y'all to come up with your own interpretation of what is a partial of f with respect to x. And just real quick, if you're taking a partial with respect to x, that means x is the only variable. That means y is fixed. You're confined to that line in the domain, aka this plane in the graph world. And, cross-section, tangent line, think through the rest of the details, right? Persuade yourself. But the punchline is going to be that the partial with respect to x is the slope of a different tangent line to the surface. Same surface, different tangent line, just kind of tangent in a different direction. All right. Okay. So, are we done? Is that all we need to understand about the geometric interpretation of partial derivatives? And, very much no. We were looking for geometric interpretation. Sure, this is the answer to what it looks like in a graph context. And that's very limited. Right? I already gave you all my soapbox speech over a couple of lectures of how graphs they're nice for occasional context when you can draw them, but very often you can't. Right? So if we're still interested in a geometric interpretation, but we can't draw graphs for whatever reason, now what do partial derivatives look like? And I'm going to show you a couple of examples. So let's suppose that I'm just understanding what a function looks like by what I like to call the literal interpretation of the function. This is a literal interpretation in that we've got this input world called the domain, and I'm going to draw a picture of it. Right? And we've got this output world where outputs from this function go into, and I'm going to draw a picture of that too. And what does my function do? My function takes points from the domain and into the target. And I'm going to draw a picture of that. So you hear that point in the domain? I'm going to let f pick that up and move that over to, there's its output point in the target. I mean, that's just kind of literally depicting what a function does. It's not a graph. We're also not really looking at level sets, and it's not a image, and it's not a parameterization. This is its own little kind of a picture, way to think about multivariable functions. Now, I will confess there's a great limitation on this point of view of the function. If you ask me, what does this picture tell me about the function f? Where can I see the function f in this picture? And very little. You can see very little of what the function is doing. I've shown you one data point, that input, and only that input, I'm going to tell you where its output goes there. We can't see how this function is, how's f changing? Is it curving around in some way, or what? There's just very little that I can see about the function here. So full confession, this is a extremely limited way to understand f itself. But it's actually a really good way to understand a derivative of f. Because remember, keep in mind, the derivative of f or any derivative of f is some sort of a relationship between input changes and output changes. And those show up very nicely on this picture. Right? So if I wanted to talk about, how should you think about the partial of f with respect to y? Well, partial of f with respect to y means I'm viewing y as the variable. That's my direction. So from where I happen to be, that's the direction I can go. And the partial derivative is a relationship, kind of a limit of a fraction, right? Y'all remember how derivatives are fun. But it's a relationship between that input change and then the corresponding, how much is the output change? It's a very natural way to think about a derivative. Yeah? Happy? Questions? Very importantly, notice it's not, in any sense, in this picture, a slope of anything, much less a tangent line. Tangent of what? It does the whole thing. It doesn't make any sense at all, right? So this is not a graph. Remember, I promised that when we started understanding calculus, once we get around to doing multivariable calculus, the calculus of derivatives, what the pictures of derivatives, what do different kinds of derivatives look like? It's gonna be different in different contexts. In the graph context, we're talking about slopes of tangent lines. in this very different picture, it's a very different interpretation. Okay. All right. Let's talk about level sets. So we've got a function f. By the way, our f here, this is the domain. F is going to take us into some target world over here, maybe the z-axis. So x and y are our input variables. Z is our output variable. Again, when we draw level sets, we draw only the domain. That's where level sets live. Level sets live inside of the domain. Okay. So in that picture, here's some level sets. Oh, come on. So here maybe is where f is equal to, I don't know, let's say 100. Right? And then this next curve here, maybe this is where f is equal to 110. By the way, so what are these things representing? I mean, these are level sets of what? If you want to think about this as representing altitude above sea level, right? And this is helping us understand the topography of the ground. Okay, that's fine, right? So, no problem. You could think of these as representing temperature. I regret the high numbers that I chose. If you want to think of this as temperature, but anyway, it's how I suppose you could, right? All right. In that setting, then, how do I think about partial derivatives? Is a partial derivative a slope of one of these lines? Absolutely not. Not even close, right? Let's think it through. Partial with respect to x here says that, from this point, I'm moving in the x direction, and as I move in that x direction with the understanding that y is constant, right? So y is fixed. Not allowed to change y. Right? We're stuck on that line. Stuck on that line as I move in the x direction. How is the function changing? And what on this picture helps me understand how x is changing? Think about your hiking experience, right? If you're hiking, and those are the contour lines, well, golly, over it seems a very short distance here, over that very short distance, I've gained 10 feet of altitude. That's steep, right? Output change per unit input change is large there because there's not much input change. It still gives rise to a significant output change. Okay. Whereas, let's think now about a partial with respect to y. Partial with respect to y means I'm moving in the y direction. X is fixed and constant. And in that direction, again, contour lines, think about hiking. I have to move quite a ways before I gain those same 10 feet of altitude. Right? So the partial of f with respect to y would be small. So, roughly speaking, an interpretation that you can take of partial derivatives, partial derivatives are inversely related to how close are the level sets in that direction. Right? And you can see as you move in the x direction, the level sets are pretty close together. As you move in the y direction, the level sets are not as close together. And then correspondingly, keep in mind those are denominators, you can infer some sense of partial derivatives from that. Kind of make sense? Everybody see how it's not a slope of anything? Okay. All right. Right. Okay. So let's talk about tangent planes. I want to rewind to Calc 1. Again, I'm a big fan, in case y'all haven't noticed, of before we do a multivariable idea, let's remind ourselves of what this analogous single variable thing was. Let's make sure that we have the context right in single variable, and then let's in the new context of multivariable do something analogous. Okay. So back to single variable calculus. The linear approximation of a function. It's this formula. I'm sure everybody remembers that formula. Make sure that you get the terminology right. I want to call this the linear approximation. Notice the linear approximation of a function is another function. Right? And another reminder, important way to think about linear approximations is linear approximations have the same value as f. They have the same derivative as f at the point where you're doing the linear approximation. Okay. All right, now, and then notice that everything that I just said there is algebraic. I'm talking about derivatives. Not talking about slopes, I'm talking about derivatives. Right? And values of the function. And we're talking about the linear approximation function. Now, the picture that you think of when you think about linear approximations, well, the picture is the graph. Right? So, if I were to take this linear approximation, and if I were to say, what's the graph of that? That's the thing called the tangent line. Well, the tangent line, that's another thing that y'all previously got familiarity with. Right, so, the graph of the linear approximation is the tangent line. Please try to exert some effort on continuing to distinguish these things, though, from each other. The linear approximation is a function. The graph of that function is the tangent line. So the tangent line is a geometric object. The linear approximation is an algebraic object. Okay. All right. So we're going to take this little story that y'all recall from single variable calculus, and we're going to kind of rip it off in the multivariable context. I'm going to suppose that I have some function, and that function at a given fixed point, I'm going to look for another function that has the same value and the same, I can't say the same derivative. Now I have to talk about partial derivatives. If there's multiple inputs, there would be several partial derivatives. So I'm going to need to adapt a little bit and say I need to have all of the same partial derivatives as the original function at the given point. And totally doable, no problem. Here's the answer. This is the linear approximation for a function of two variables. For the moment, I'm just going to talk about multivariable being two input variables. So you'll even notice that structurally this is not that different from the single variable formula. Structurally, there's kind of the starting value, if you will. Right? And then, it's so derivatives have to get multiplied by input changes. That's kind of sort of the idea in single variable context. So we're going to do that same thing. It's just that I'm going to do it in sort of two separate steps. There's derivative in the x direction times how much x changes. But, I mean, not everything's happening in the x direction. There's also derivative in the y direction times how much y changes. So, just structurally, the formula is pretty familiar looking. It's not that different. That structural similarity, I emphasize, though, is not the point. The point is, and I want you all to check this on your own. It's an important exercise. Everyone should do this. This function has the same value as f. If you were to plug in the point a comma b, L of a comma b is equal to f of a comma b. It's got that same value. And furthermore, if you were to take the partials of L, take the partial of L with respect to x, take the partial of L with respect to y, you're going to get the exact same value as the partials of f with respect to x and y. Okay, so again, do that exercise. It will be analogous to the exercise that you all probably all did in a Calc 1 class of confirming that this function, same value, same derivative. Alrighty. So, Now, what did we do in the single variable context? Once we had a linear approximation, we said, hey, let's look at the graph and call that the tangent line. Old news. Well, now we have a new linear approximation. This is a multivariable linear approximation, but same deal. Let's take the graph of that and let's call it tangent something or other. And let's think that through what we're going to call it, though. The graph of that L there's the picture, or there's the algebra of a graph, z equals L of xy, and if you look at the structure of that equation, z equals, plug in what the L is on the other page, that's the equation of a plane. So let's not call it the tangent line by analogy. That wouldn't make any sense. It's the tangent plane, because that's what it is in this new context. Everybody good? All right, and tangent makes a lot of sense. I mean, kind of the motivation in some, it depends on how you look at it, but a motivation is that this line with that equation and our original graph with that equation, you can say it in different ways. This tangent line tracks the graph of f. It's sort of mimicking geometrically. It's staying as close as possible, however you want to say geometrically what it means to be a tangent line. But same thing here. This plane is, you might want to say it side swipes the surface. That is the original graph that I was looking at, or it's the plane that as much as possible stays as close as possible to that plane while you're near the original point you're looking at. Yeah, depending on how you want to say it, but it's got that same kind of feel about it. Everybody good? Okay. All right. Okay. What if you have more than two input variables? Now, this is just a matter of kind of writing down the same kind of algebra. It's a little bit, you got a notation and stuff, but it's morally equivalent. If you have more than two input variables, the algebra is just not that different. There's a linear approximation of a function of several variables. Now, let's not talk about the picture. I don't want to try to draw. So, the graph of this linear approximation, what does that thing look like? I don't know. It's high dimensional. I mean, if it's more than two inputs, there's at least three inputs, there's one output, it means at minimum we're talking about a four-dimensional picture if you want to draw a graph. I'm not even going to try to fake that I could do that. Right? So don't think about this geometrically, but algebraically, it's not that different. Again, easy to check. This function here has the same value as f at the given base point. And it has all of the same partial derivatives as f for algebraically pretty much exactly the same reasons. Okay. So, linear approximation, just as good in higher dimensions. Okay, so let's talk about what partial derivatives look like if you do more than one of them, so higher order partials. Now, y'all remember second derivatives, for example. Right, so second derivatives in single variable calculus. And you remember second derivative relates to concavity. Y'all remember all that business, concave up, concave down, plus, minus stuff. That's still true for multivariable functions. I'm going to draw by the way, we're going to look only at functions of two input variables, just two, so that I can talk about the whole point of this is I want to be able to talk about the geometric interpretation. I can only give you a geometric interpretation in the graph context if I can draw the graph, so we're stuck with two input variables. And first observation, let me just point out algebraically, if you want to take a higher order partial, okay, go ahead. There's nothing stopping us, right? In other words, if I start with this function, if I take a partial with respect to x, note that what I get is still a function of x and y, and I can talk about its partials just as well as I could talk about the original function's partials. Same process. Okay, so a couple of examples. By the way, while I'm here, let's talk about notation a little bit. This is an alternative notation for a partial derivative. Y'all will recall that with single variable derivatives, we talk about df dx, and we also talk about f prime. And pros and cons on these notations. The nice thing about this notation is very compact. It's convenient. It's not to be underappreciated, right? That's non-trivial. The nice thing about this is, in certain contexts, algebraically it looks nice, and let me not go down that road for the moment. But so the pros and cons on both of these notations. Well, in the same way that this is kind of a analog of that, and similarly, an analog of Newton notation would be something like that. And I mean, why can't we just say f prime? Well, in single variable, you could say prime, because prime just means derivative. You don't have to ask derivative with respect to what. There's only one input variable. Take the derivative. It's just the one. Right? But prime wouldn't make sense in this context because, well, there are two input variables, and you mean derivative with respect to x or y. Right? So we get around that by just making the variable in question a subscript, and it's pretty reasonably convenient to write down. Okay, all right. Also on the topic of notation, and this is awkward, but let me write it down. In fact, let me zoom in so I can. Let's look at if we were to take. Again, taking the x part. Oh, what happened there? Taking the x partial of that x partial. Well, let me write that down sort of more explicitly. We're taking a partial with respect to x of a partial with respect to x of f. Right. So that's kind of that's one way to write down what we're looking at there. And this always gives me the willies, but. It's like there's two partials there, and so they write partial squared. Again, it gives me the creeps because we're not actually multiplying partial symbol by itself. That's just not what that means, though. All right, so it's very common notation, and you're going to totally see that a lot. So anyway, be prepared. Likewise, this thing here, this is not intended to suggest that I'm multiplying partial x times partial x. It's just that it's there twice in the notation. So notationally, it's as if, but of course, don't interpret that squared literally. Yeah, everybody good? Okay. Right. Okay. So the actual calculations of these partial derivatives are just a matter of plug and chug. Now you might have noticed that this one and this one happen to be the same. Right? So what's going on there? Is that a coincidence? You can kind of see maybe by the way how with polynomials, sort of that's the way you're going to multiply. It's going to happen with polynomials. It's not hard to see, but it's true more broadly than that. So this is a deeper point than it appears to be. This is not sort of symbolic manipulation coincidence. Any function that is sufficiently nice, as long as the partials or second order partials are all continuous, which again, most functions that we're going to deal with are nice functions. This is going to happen most of the time, right? Then it doesn't matter which order you take the partials. fxy, fyx, same thing. Okay, that's kind of neat. Okay, geometrically, what do these look like? And good news, kind of familiar, at least to get started. Let's talk about, here's a function. Now again, notice I'm looking at a graph. You can see we got a domain down there, target here. So just for emphasis, let me write down, so z equals f of x, y. So we're looking at a graph here. Emphasize graph. In this graph context, z being a function of x and y, we can make pretty good sense out of what partials, second partials look like. For example, let's think through fxx. And so what does fxx, how do I compute fxx, and from that, what would I interpret about it? And remember, the way you compute fxx, first you take an x partial, then you take an x partial, and then you there you go. There's your second partial with respect to x. Keep in mind, in that process, when you're taking a partial with respect to x, you are fixing x. You are restricting your attention just to that cross section right? That cross-section of your original graph in that plane. And having taken that first derivative, you then take another x partial, which means continue to hold. I drew the wrong. Look at me. I'm sorry, man. I'm sorry. We're taking a partial with respect to x. That goes this way. Sorry about that. We're holding y constant, going in the x direction, holding y constant. So we are stuck in this plane. There's our cross section. And having taken our first x partial, we then take another x partial, which means for the purposes of both of these derivatives that we're computing here, y is constant. For the purposes of both of these derivatives, we're stuck in this same cross section. For the purposes of both of these derivatives, we're looking at that slice of our original Pringle graph. Right? So, we're taking a single variable derivative of what I can interpret as being a straight up graph of a single variable function inside of that cross section. So in fact, this is the wonderful punchline. If you're taking a partial with respect to a second partial, both with respect to x, you're going to get the same concavity interpretation that we had in single variable calculus. This is just concavity, and you can see that this one here is this is clearly concave down, and so negative. Does that make sense to everybody? Sorry I had it backwards first. I'm sure I had it all confused there for a second, but anyway, there we go. Okay. Right. Ditto in the for the y partials, right? If you're doing a y partial with respect to y, so you're moving only in the y direction. X is constant, fixed. You're looking in this plane, looking at that cross section. Second derivative, concavity. Concavity is clearly up. Positive. Okay, so strong analogy. That's really nice. Now, but what about these mixed partials? And what happens if you're looking at a y partial of an x partial, or an x partial of a y partial? Here I can't just say, oh, well, you're taking a cross section. Fix x. Go about your business. Right? Because for the purposes of that y partial, yeah, here we're fixing x, right? But then having done that, we are then saying explicitly, now let's let x move. Right? So this whole, oh yeah, it's just like single variable calculus, out the window, right? This is totally different. So here's how we're going to deal with this. It's just a matter of taking the right interpretation and the right part of the calculation. We're going to look at the y partial, and then we're going to take an x partial of that. Recall, one of my interpretations of partial derivatives is that y partials means that I'm looking at a slope of a tangent line in the y direction. That's one of my interpretations. Right? So we'll start off thinking about slopes of tangent lines. When I get around to taking the x partial, forget about slopes of tangent lines for this x partial. We're not going to interpret the x partial as slopes. We're going to think of the x partial as a rate of change while you're moving in the x direction. Right? That's one of our other interpretations. So here we go. Now I'm going to show you a picture, and the picture is really awkward and hard to draw. So this is kind of the best I can sort of reasonably do. But slopes of tangent lines in the y direction. In the y direction, right? Depending on where I am, these are a bunch of different ways that I can move in the y direction depending on where I am in the domain. As you move in, the y direction, you're going to have these tangent lines like that. So you'll be looking at those tangent lines. And I want to know, though, how do those tangent lines change? Specifically, how do their slopes change as I move in the x direction? So I'm going to be moving that way, right? As I move in that direction, I want to know how these tangent lines' slopes are changing. And this is
Hard to, like I say, hard to draw a picture, right? So let me 3D model with my hands. Remember, the x-axis is coming out of the board, right? So here my hand is representing this back tangent line, right? And now as I move in the x direction, as I come out of the board, I'm going to try to represent how this tangent line in the y direction, how its slope is changing as I go in the x direction. And so it's kind of like this. Right? Everybody see what I'm talking about? Now this is my attempt to draw it, and it's hard, you know. Right? But anyway, so let's just think, well, what does that look like? I mean, what does it look like if a surface kind of, as you move one way, the slopes in the other direction are kind of changing? And I think if you were to just, you could sit there and do this with your hand, right? If you just kind of do like this and ask yourself, what kind of a surface are you kind of tracing out there? There's a surface that kind of has a sort of a twist in it. It's like you have a flat sheet of rubber and you're going to kind of do like that. It's like you're going to grab it on the corners, right? And you're literally going to put a twist into it. So that is what mixed partials represent. Unmixed partials represent concavity. Mixed partials represent twisting of the graph surface. Okay. We'll call it a day right there. And very little bit more that I'm going to say about this, but we'll do that on Wednesday. So see y'all later. Have a good Monday.